this is kind of a neat little thing that goes along with binomial. It's a normal approximation to a binomial distribution. Now, just for review's sake, remember we have 4 rules of a binomial setting: success or failure, fixed number of observations or trials, all of your n observations must be independent, and the probability of success is fixed for or is the same for every observation. So remember, this needs to be committed to memory if you haven't already. And we are able to come up with a mean for a binomial random variable, n times p. Variance is n times p times 1 minus p, which makes the standard deviation the square root of n times p times 1 minus p. So these you need to know also. Okay, here we go. So for a binomial random variable, if n times p, which just so happens to be the product that we use to calculate the mean, if that is greater than 10, and if n times 1 minus p is greater than 10, then x has an approximately normal distribution. Okay, that's a pretty big stretch, because a binomial random variable is not continuous, it's discrete. So we're actually forcing a discrete model into becoming a continuous one. And so we're going to have to pull off a little trick along the way to sort of make that happen. All right, and here is the trick. So if you are calculating the probability of your binomial random variable x being between 2 numbers, right, or between and including, what we have to do is calculate, or do a little conversion here. We're going to have to take that lowest number and subtract 0.5, so it becomes an even smaller number, and then minus mu over sigma. That'll be less than or equal to z, which is less than or equal to your upper value in this interval with 0.5 added to it, minus the mean over standard deviation. So you get the area under the normal curve between a minus 0.5 and b plus 0.5. All right, what is this minus and plus 0.5 all about? This is a continuity correction. In other words, it's taking something that's discontinuous and forcing it into something that is continuous. So the correction creates continuity. So for example, let's just say we're, well, in college when I went there, we had some kind of, I don't know, some industrious student of some sort had betting slips, and there were 20 college football games, and if you were able to, I think, pick 15 out of 20 correctly, you won like $5. You bought the ticket for $1. If you won every game, or if you picked every game correctly, then you won like $100. Well, the thing is, nobody even won $5, because basically sports is witchcraft, especially college football, because on any given weekend, the lowliest of teams will rise up to smite the mightiest of teams. So you would be picking, you'd never pick them correctly, even 3/4 of them. Anyway, let's just say we're going to approximately pick between 12 and 16 games out of 30 when the probability of picking correctly is 0.5. All right, that's sort of a stretch, but just for sake of having an example, let's go with it. All right. First of all, you have to check that condition. Is n times p greater than 10? Is n times 1 minus p greater than 10? And it turns out that in this case they are. Now, it's really important that you check this, because if you don't, it may be that one of these two products is less than 10, you don't know it, then you're going to force a model that's inappropriate into becoming normal, and it's just going to be a lot more work than if you just, do regular binomial PDF or CDF, because that's what you have to do if you're not able to do a normal approximation. And doing a binomial PDF and CDF is way, way easier. All right, So calculating the mean, of course, it's going to be the same as this. Standard deviation is this. All right, so then you take 12 up to 16, you subtract 0.5 from 12, which is 11.5, you add 0.5 onto 16, which is 16.5, and then you just go ahead and create z-scores as you normally do. And you go to normal CDF and you get an approximation for that binomial probability. And you might want to go ahead and just do the binomial probability to see how close it comes. In this case, it was only a little bit off. Now, of course, you don't need to do this kind of subtraction method on an n-spire. You're just going to go from 11, I'm sorry, you're going to go from 12 to 16, but it's going to come out to this anyway, and that's only slightly different. So that's a great approximation. All right, between 16 and 22 games correctly. All right, 16, subtract the 0.5, 22, add the 0.5, standardize, normal CDF. Now, if you were to just do binomial CDF, again, pretty close. All right, so between 16 and 22 games correctly, the probability of that, now keep in mind they're not including 16 or 22. So you're going to have to do just a discrete correction first. All right, that's really what we're talking about. It includes 17 to 21, right? Here we are just not including the 16 to 22. So make this correction first, then continuity correct. All right, so we're going to use this correction, and then we're going to take half off of the 17, add half onto the 21, standardize, get a z-score, do a normal CDF, and that's your comparison. All right, this is what's really going to kind of blow your mind. If you flip a coin 30 times, what's the probability of getting exactly 15 heads? Well, you shouldn't be able to do that with a normal calculation because there are no point estimates in a continuous model. Remember that? Remember that the probability of any one number was 0, but the probability of between a couple of numbers did give you actual answers besides 0. All right, you can still do this. You're just going to check it, OK to proceed, get your mean and standard deviation. All right, again, no point estimates unless you do a continuity correction, which means you treat this as both the low number and the high number. Right? So it's really going to be between 14.5 and 15.5. So just standardize, get a couple of z-scores, normal CDF, compare that to your binomial PDF. It's only off by a few, tens, hundreds, thousands, a few 10,000ths of a point. Okay, so why do this continuity correction in the first place? Here's what we would look at if we were to kind of, graph this as a continuous model, because remember, I'm sorry, not as a continuous, but as a discrete model. Remember that in a discrete setting, all of your probability is right at the particular whole number value, and there's nothing in between. So probability of 5.5 is 0, probability of 1.2 is 0. Okay. So what we're going to do is we're going to take this low number and subtract a half and do that to all the numbers, right, all the way up to 7. Then we're going to take this number 0 and add a half and do that to all the numbers, and we end up filling in and making an area model, right? So now this thing is made up a bunch of rectangles and has area. And if you superimpose a normal curve over it, then you're doing an approximation. Sometimes this model is going to cut into it, sometimes it's going to poke out of it, but in general, it's a pretty good approximation. Okay, so your homework is going to be the worksheet on normal approximation. Please check your conditions first. Make sure that n times p and n times 1 minus p both exceed 10. If you fail to do that, you're going to be answering a whole lot of questions with a normal approximation, and it's going to be a bit more work than if you just aren't able to do it, and you're going to just do a binomial PDF and CDF instead. All right, so you've been warned. Give it a shot. Everything's posted. See how it goes. It's not that hard. Just make sure you correct for just the less than or greater than without the equal to, then do a continuity correction from there, and it should be pretty easy if your normal calculations are up to speed. So we'll get out of this, and I'm going to close out, and we'll see you next time.